Physics 100. I am Professor Curtis, your instructor for this course, and this is the lecture for Chapter 12, Solids. Let's get started. So now that we've examined the basic characteristics of matter and how it's structured, we're going to investigate further for different states of matter. And the first state that we're going to examine is the solid state. Solid material has various characteristics. The atoms of the material are vibrating in place, have little to no movement relative to each other, so they're more or less, it's like everyone's in their house and they're just being super active, but they're in their house and they don't go anywhere. This is material in the solid state. Now, from an engineering perspective, there's 5 different groups or classifications of solids. First, we have metals, and these are elements like iron, aluminum, tin, gold, zinc. The list goes on. And then we've got ceramics, which are basically oxidized metals. And these are your stone, your brick, other refractory materials. Then we've got polymers, plastics, resins, rubber. These are the materials that stretch and bend and form. If you've ever had silly putty, played with silly putty or Play-Doh, these are examples of polymer materials. Biological materials, so these are materials that are structured in living organisms. So we've got fibers and cells and that sort of thing. And then we've got composites, which are just combinations of the previous 4. So you could have, say, reinforced concrete is a good example of a composite material. You've got metal steel rods that are encased in the ceramic concrete. So you've got the concrete and the metal together. That's going to give you a composite material because it's not just a metal or a ceramic, it's got both. Now, some solids are what we call amorphous, but most are what we call crystalline. What does this mean? Well, amorphous means that the atoms have no set arrangement, so they're just randomly thrown together there in the material. Crystalline means that the atoms are arranged in an ordered pattern. And this ordered pattern is what we call crystal structure. This was discovered in 1912 by Max von Laue, who you see here, a German physicist. And of course, 1912, so this is just before World War I breaks out. And basically, he was looking at X-rays, and this was very popular. I mean, after Roentgen discovered X-rays in 1895, X-rays were a hot spot in the scientific community. And so everyone who wanted to do cutting-edge research was doing something with X-rays. And von Laue was no different. So here he is. He's got X-rays, and he's shooting them into thin slivers of material, and the X-rays are going through, and they're forming a geometric pattern on the photographic plate that he places on the other side of his specimen. And he noticed this geometric pattern that appears on the plate. And the only way that you could get a geometric pattern is if the individual atoms inside the material are organized according to the same geometric pattern. And so because there was this ordered pattern to the material, this has to be the source of the diffraction. And this is what gave birth to the idea of crystalline materials. As further research was done into this topic, it was shown that most materials do have a crystalline structure. And this is especially true of metals. There are very few examples of some metallic glasses which are amorphous, but as a general rule, metals are crystalline solids. They have crystal structure to them. Now, before we go on, I just want to make a mention about a historical note with Mr. Laue. So, Max von Laue, look at him. He's German. And look at when he was born and when he died. So he lived through both World War I and World War II. If you want a profile in courage, Max von Laue is your man. Because here he is. He's a German physicist, and most of his colleagues, as the Nazis were gaining power in the 30s, found their way outside of Germany. Many of them left, especially those who would be persecuted by the Nazis or who had political disagreements with the Nazis. Von Laue is an exception to that rule. He had strong disagreements with Hitler, and yet he stayed in the country. Now, if you know anything about the Nazis, you know that if you disagree with them, you don't want to be staying in their country because they're not going to take your disagreement lightly. And yet, they didn't touch Von Laue because he had like really good stock German ancestry. I mean, you want to talk about like Aryan perfection? This guy had it. And so they weren't going to touch him because of that. But yet there were so many people who wanted to just scrap that and say, look, he's talking out against the Fuhrer. You know, we've got to put an end to this. And yet they wouldn't touch him. So a lot of courage this guy had, staying in his home country while the Nazis were ruling and actually being very vociferous in opposition against Hitler. So if you want to profile in courage, Von Laue is your man. Now, on this idea of crystal structure, we produce, distinctive X-ray patterns, and we use this diffraction pattern called X-ray diffraction, XRD. And this is actually a tool that's still in use today for many of the biological and physical sciences. So essentially what we do is we basically bombard the surface of the material with X-rays, and typically the specimen is going to be in a powdered form. So we grind the material into a powder, and then we put this powdered sample in the machine, and we bombard it with X-rays, and the X-rays deflect off at given angles and form a certain pattern on a photographic plate, and then you can look at that geometric pattern that's formed and tell what crystal structure your material has. And then the different sizes of the lattices, so the different, how big your crystals are is related to the different size of elements, because every element has unique dimensions for its crystals, its structure. So you can use this to identify not only what crystal structure the material has, but what element is there in the material. For metals, you've got three basic crystal structures. There's 14 that we know about altogether, but most metals have one of these three crystal structures that you see here: body-centered cubic, or BCC, face-centered cubic, or FCC, and then there's hexagonal closed pack, which is also abbreviated HCP, hexagonal closed packed. And you can see the different types of example materials that they give here. So iron and vanadium and niobium and chromium are good examples of body-centered cubic metals. Aluminum, nickel, silver, copper, and gold all have a face-centered cubic structure. And then some of your more specialty metals like titanium, zinc, magnesium, cadmium, these have hexagonal closed packed structures. And these are the ones that we see most commonly in metals. Now, the reason why all of this matters is that the way your atoms are positioned and arranged at the microscopic level will determine the properties that you see in the material on the macroscopic level, which is the level that we live at. Different crystal structures and different spacings between adjacent atoms will give you different levels of strength, ductility, hardness, and toughness. So a lot of the mechanical properties that a material has is determined by its crystal structure. The crystal structure also correlates very well with thermal properties, such as the melting point of the material. So if you look at materials that have low melting point, materials like lead, aluminum, gold, these materials have face-centered cubic crystal structure. And then the ones that have a more moderate melting temperature, like iron and niobium, these are body-centered cubic metals. And then typically the ones with the highest melting points are the ones that have the hexagonal closed pack. So metals like titanium have a high melting point, in large part because of its hexagonal closed packed crystal structure. Forces act on solid materials in different ways. So there's different types of forces that can act on a solid material. We can have tension, which are forces that pull apart on the material. Or we can have compression, and this is where forces are going the other way. They're actually pushing the material in. Then you have bending forces, which are forces that bend the material. And then you have torsion forces, which are forces that twist around a certain axis. So you've got twisting one way on one end, twisting the other way on the other, and this puts a torsional force on your material. Now, because Newton's third law says that for every action there's an equal and opposite reaction, so each of the forces that you apply to a material externally will create an internal resistance force as a reaction to the force that you apply. Remember, action-reaction forces always occur in pairs. So when you apply one of these forces to an object externally, there's a reaction force internally to the material that is developed, and it's equal and opposite to the applied force. Typically, solid materials that are have high strength and tension have poor strength and compression. This is particularly true of, say, a lot of metals. Some metals have really high strength and tension. For example, aluminum is a good example of a material that it's harder to pull apart, especially if you get some good thickness into your specimen. But if you try to push it together, you don't need as much force to compress it and get it to deform as you do to pull it apart and get it to conform. So high strength and tension typically has poor strength in compression. The reverse is also true. Typically, materials that are high in compression strength have low tensile strength. Concrete, cement are good examples of this phenomenon. Many of your ceramic materials like brick and stone, really good in compression, so they can bear a lot of weight on them. But if you try pulling them apart, you don't need as much force to pull them apart, but they can withstand a lot more force on the compression side of things. So high compression strength typically means low tensile strength. Materials with high strength that are either tensile or compressive tend to have higher melting points, and low strength materials tend to have lower melting points. Think, for example, about lead. Lead has a particularly low melting point, and yet things that are made out of lead are easily malleable under the right conditions. I mean, you could shape lead with your fingers under the right conditions, and so very soft material. Gold's the same way. Gold has a very low melting point relative to most metals, and this is one of the reasons why gold is so valuable, because it's easy to see what gold is. It's soft enough that you can deform it pretty easily. So people in the old days that were biting on gold coins to verify that they were made of gold, yeah, I mean, gold is softer, and that low strength is related to the low melting point of the material. Well, what is it would connect the two together? Why would a low-strength material tend to have a lower melting point? And the answer is crystal structure. The crystal structure of the material. Remember what we said before about crystal structure determines mechanical properties. Crystal structure determines thermal properties. So the two are related through the crystal structure. How the atoms are arranged microscopically determines how the material behaves macroscopically. Let's consider bending forces for a moment. Solid materials under bending forces are experiencing both tension and compression. This happens in different parts of the material. So if we have, for example, look at the bending test that's being performed on the reinforcement rod there in the photo. So you've got two, I guess you'd call them supports. They're on the bottom and they're stationary, and then there's a third one there in the middle, and it's actually attached to a moving piston, so it actually goes up and down, and when you press the go button, then it actually pushes down with a certain amount of force, and you can pre-program it to have whatever force you want, have the force applied at a certain rate, however you want to do this. When you press the go button, it goes, and there you see eventually the bending strength of the material is exceeded, and there's a bend there in the material. Now the side that's closest to the center of curvature is in compression, and the side farthest from the center of curvature is in tension. So the center of curvature, if you imagine the curve in that bar being part of the circle, the center of that circle is the center of curvature. So the side of the bar that's closest to the center of curvature is the side that's in contact with that moving ram, the piston. That's the side that's touching that ram piston. And that's a side that's in compression. So if you think about the material on that side being pushed together towards that bend, that's why it's in compression. Whereas on the flip side, on the opposite side of that bar, the side farthest from the center of compression, that's in tension, because there the material's being pulled and stretched apart. Those are tensile forces. So the side closest to the center of curvature is in compression. The side farthest is in tension. Again, notice how nature is still balanced out when the material is deforming. There's compression on the one side that's equal and opposite to the tension that's on the other side. Now, halfway in between, you get what's called the central axis of the material. And this is what we call the neutral layer, because here the material experiences no force whatsoever. You've got maximum tension on one end, maximum compression on the other end. So halfway in between, in the center, you've got nothing going on. Everything's perfectly balanced out. Nothing's in tension or compression. There's zero force there at the center. And this effect is partly why I-beams have the shape that they have. So we want the outside, we see where the material has the flanges, that's where it's the widest. And so that's where you're going to bend an I-beam. You want the highest forces to be where you've got the most material. But there in the center of the I-beam, along that central axis where you don't have a lot of material, you don't need a lot of material because there's zero force there in the center of the material. So all the forces on the I-beam when it's in bending are on the outside flanges. And that's why the material in part, there's other reasons why, but this is part of the reason why the material is shaped as it is, the I-beam is shaped as it is, because you don't have any force there at the very middle, and so therefore you don't need a lot of material. Any material you have there is just wasted because you don't need a lot of material to resist zero force. And finally we have torsion. Torsion is just like bending, but we're orienting it in a different motion. So if we look at, say, like a bar that we're twisting in opposite directions on each end, and we look at it from the side view here, so now we've got maximum tension is being experienced in the middle of the bar, and then maximum compression is there on the opposite ends of the bar. So this is the same thing we see in bending, just oriented a little differently. And of course, halfway in between the tension and compression zones, you've got zero force. So you've got two places here in the bar where you've got zero force acting on the material. This brings it to the concept of elasticity. Because when we apply a force to a material, the material can behave in one of two ways. It can behave elastically, and what this means is you apply the force to the material, and then when you take the force off of the material returns to its original dimensions. So think of it like a rubber band. And although it's really hard to see with the naked eye, many metals that are crystalline in structure behave elastically up to a certain limit. Beyond this limit, which we call the elastic limit, the material will behave inelastically, meaning it's not going to return to its original dimensions when you remove the force. There is some permanent deformation that you've introduced into the material. Now, as I was just saying, many materials have what's called an elastic limit. So as long as the stress or the force that you have imparted to the material is below that elastic limit, then you can apply the force, the material will stretch out or deform, and then when you let go of the force, release the force from the material will return back to its original dimensions. And there will be no permanent deformation in the material. But if you exceed that limit, exceed the elastic limit, you're going to introduce permanent deformation in the material once you release the force from your material. Now, on a microscopic level, the crystalline materials are behaving just like a spring. And so, as long as you're underneath that elastic limit, you're within the elastic limit of the material behaves very much like a spring. You put a force on it, it stretches out. You take the force off, it snaps back into its original shape. So this is what we see with forces. I mean, with the spring, right? So you apply a small force, and then you take the force off, and then the spring will bounce back to its original position. But if the force is large enough so that you exceed the elastic limit, then the spring doesn't bounce back all the way. That's because it's past its elastic limit. And now you have what's called plastic deformation. So there's elastic deformation, which is, it disappears once you release the force off your material. And then there's plastic deformation, which is that's deformation that remains in the material after you release the force. And plastic deformation means that you've exceeded your elastic limit, because that's the only way you can get plastic deformation. The scientist that was really instrumental in giving us a lot of the groundwork behind elasticity is Robert Hooke. Robert Hooke was an interesting character, a very noted scientist, contemporary of Sir Isaac Newton, and this was, I guess you might say, part of his downfall, because Hooke and Newton just did not get along all that well. If you've ever been around somebody, it's not so much of what that person says or does that irritates you. It's just them being them. And just being around them, it just annoys you, runs across your grain. That's the way the relationship between Hooke and Newton was, although they turned it into a rivalry that went into extremes. Well, of course, both of them noted scientists in their own right, and because they were noted scientists in their own right, they both belonged to the preeminent scientific organization in England at the time, which is the same today. It's the Royal Society of London. And, eventually there came a time when the president of the Royal Society died, and so they needed to appoint a successor. Well, guess who got appointed to be the next president of the Royal Society? It was Sir Isaac Newton. And Newton, of course, being so incensed with Hooke, immediately proceeded to obliterate anything that had anything to do with Hooke. So even the picture that you see here of a portrait that is supposedly done of Robert Hooke, we're not really sure that it's him, because Newton had every painting of Hooke that he could find burnt. Many of the notes and papers that Hooke had published were also burnt and destroyed. So there were some people who saw what was going on and decided that, no, some of what Hooke did needs to be preserved. And so that's why we know about what we do know about Hooke. But much of what he did, and even what he looks like, we have no clue about what was going on because of Sir Isaac Newton. Yet another way in which Newton was influential in the history of science. So one of the things that we do know Hooke for was his experiments with springs. And one of the things that he observed was if you increase the tensile force on the spring, you get a greater displacement. In other words, the spring stretches out more. Well, he noticed that you get different displacements for the same force if you change the material of the spring. And this observation led him to postulate what today we call Hooke's law. Now, the correct designation of Hooke's law is what you see here on the screen. F equals negative K times delta X, where F is the applied force. In Newton's, K is a spring constant. It relates the stiffness of the spring, and that's in units of newtons per meter. And then delta X, which is the change in X, is the displacement of the spring, how far out the spring is going to stretch, and we measure that in meters. Now, notice that everywhere that we go, okay, except in the textbook from your textbook author, okay, everyone uses that negative sign in front of the constant. Because this is a general survey class, we're just going to use the equation without the negative sign. And we can get away with this because we're going to absorb that negative sign into our definition of delta X. So we're going to define delta X where we're looking at the distance between the elongated length minus the length of the spring at rest without any extra force added onto it. That's how we're defining the change in displacement. And so we're going to use this formula without the negative sign. The negative sign is actually essential to be true to the sign conventions that we saw earlier for vectors. Because remember, force is a vector, displacement is a vector, so we've got to be concerned about direction. And that's why the negative sign is there, because normally with the way we define delta x, the applied force is acting in a direction opposite to the displacement vector. But we're going to define delta x so that we don't need that negative sign out in front. So this is the equation that we're going to be using for all of our example problems, homework, and whatnot. F equals k delta x. Speaking of using this equation, let's look at an example right here. Imagine that you have two springs identical in every way except they're made of two different materials. So the materials are different, but everything else about the springs is the same. So the springs have the same length, the springs have the same number of coil turns, the diameter of the coil is the same. Everything about these springs is the same except the material they're made of. So we're going to take a 10 Newton force and apply it to each spring. So there's spring A and spring B. And spring A extends 0.02 meters, which is 2 centimeters. But spring B extends 0.05 meters, or 5 centimeters. Upon removing the 10 Newton force, both springs return to their original length. So we haven't exceeded the elastic limit. The deformation we're imparting into the spring is elastic deformation, because once you take off the force, the material returns back to its original size and shape. First question we have is, what is the spring constant for each spring? Second, which spring is stiffer? And 3, what does the spring constant tell you about the stiffness of material? Let's run through this step by step, and so you can see how this is actually going to play out. So what is the spring constant for each material? Well, let's look first at the spring constant for spring A. So we're going to take K and put a little subscript A on that to be the spring constant for spring A. So we start off with Hooke's law. F equals K, and this is our spring constant is going to be Ka times delta x. Next, we substitute in what we know. So we've got a 10 Newton force. We don't know what the spring constant is. That's what we're trying to find out. And then the change in x is the elongation. So we measured it out to 0.02 meters. And we subtract out the original length of the spring, which is 0.01. Now we subtract those two out, and that gives us 0.01 meters. And then we can divide both sides of our equation by the 0.01 meters to leave Ka all by itself. So the 10 newtons divided by 0.01 meters gives us 1,000 newtons per meter. Go ahead and stop the video here and see if you can follow along the same calculation path for the second spring, spring B. Then when you get done, come back and we'll see how well you did. Okay, let's see how well you did with the spring constant for spring B. So we're going to use a subscript B for our spring constant. We start off with Hooke's law, F equals K times delta x, and our spring constant is Kb. We've got the same 10 Newton force, but now notice how spring B extended out to 0.05 meters, and its original length, 0.01, so we subtract that there. And that gives us 0.04 meters, or 4 centimeters. Divide both sides by that, and then 10 divided by the 0.04 gives us 250 newtons per meter. Now, which spring is stiffer? Well, obviously the spring that's stiffer is the one that didn't extend as much for the same force, and that's going to be spring A. So spring A is stiffer because it displaces the least. Now look at the difference in the spring constants. Spring A is stiffer and it has a higher spring constant. So what we learn from this is that the higher the spring constant, the stiffer the spring. So this spring constant actually relates a relative idea of how stiff the spring is. Now that we've examined elasticity, let's look at the concept of density. Earlier we mentioned that the spacing between individual atoms in a material influences the macroscopic properties of that material. Well, microscopically, we can measure that atomic spacing with X-ray diffraction. Macroscopically, though, the measurement that we use is density, how packed in the atoms are relative to each other. And so this is what density is. We represent it with the lowercase Greek letter rho. I know it looks like a P without the little serif tail on the top there, but this is actually a Greek letter rho, and yeah, and that's how you pronounce it, rho, as in row, row your boat. Well, that's a different rho, but anyway, Greek letter rho, and it's equal to mass divided by volume. So m is mass and v is volume. So mass divided by volume is density. For solids, density is a material property. What that means is that the property is determined by the type of material that you have. And it also means that if you have the same material, the density is going to be the same. So you could have two different objects, but if they're made of the same material, then the density of each of those objects is going to be the same. We measure density in kilograms per cubic meter or grams per cubic centimeter, with the understanding that 1,000 kilograms per cubic meter is the same as 1 gram per cubic centimeter. Let's get a feel for how density varies for solid materials. So here we have an activity that we're going to run through, and I'm going to give you an example of how this is going to run. So let's say we've got 584.8 grams of tin for every 80 cubic centimeters of tin. So this is what we're given, and we need to find the density. Well, remember, density is just mass divided by volume. So we take the mass, 584.8 grams, and divide it by the volume, which is 80 cubic centimeters. And we get 7.31 grams per cubic centimeter. And that's all there is to it. So the density of tin is 7.31 grams per cubic centimeter. So now what I want you to do is, on the next page in your workbook, go ahead and look at these examples that you have there, and for each of them, calculate the densities for each of those examples. And then once you have that done, go ahead and rank them from largest density to smallest density, and see if we can identify any patterns in what you see with the ranking. Go ahead, stop the video and take care of that, and then when you get done, come back and we'll see how well you did. All right, let's see how well you did with this. So here are the different examples that you should have calculated. And to review how to calculate each one of them, for the oak, we'll just look at them in the order they're presented. So the oak is going to be the 85.2 grams divided by 120 cubic centimeters, which is 0.71 grams per cubic centimeter. Aluminum, 2.7 grams per cubic centimeter. Pine, 0.37 grams per cubic centimeter. Silver, 10.5 grams per cubic centimeter. Styrofoam, 0.08 grams per cubic centimeter. Concrete, 2 grams per cubic centimeter. Nylon, 1.15 grams per cubic centimeter. Gold, 19.32 grams per cubic centimeter. Iron, 7.87 grams per cubic centimeter. When you rearrange them and rank them from largest to smallest, here's the ranking that you see here. So gold is first because it has the largest of all the examples there, and then silver, then iron, then aluminum, then concrete, nylon, oak, pine, and styrofoam. Now, do you notice any patterns or trends in the ranking? Look carefully at the types of materials that have similar densities, or similar relative densities. So you've got different neighborhoods here that we're looking at. And if you notice, the ones with the largest densities are all metals. And then we find we have ceramics, in this case there's only one, concrete. And then the remaining materials are polymers or composite materials. So here we've got a trend that we notice that generally speaking, metals have higher densities than ceramics, which in general have higher densities than polymers and composite materials. Now, this is just a generality, okay? There's obviously some exceptions to the rule, but the general rule is what you see here. Metals have the highest densities, followed by ceramics and then polymers. And that brings us to the end of this lecture. I hope you found it helpful. Thanks for watching, and we'll see you in the next video.